Good afternoon, everyone. Welcome to our webinar today. I wanted to, before we get started, I just wanted to cover off some logistical pieces here, specifically that we're going to have everyone in listen-only mode, as we've had well over 100 people register for the webinar, so we've got quite a large group of folks coming. And so rather than being able to ask questions during the webinar, we will have a question and answer period at the end. And so if you have any questions, please feel free to use the question pane in the dashboard. So just type your questions in there, and then I'll pass those along to both Andy and Michelle at the end of their presentations. Also wanted to let you know that this webinar is being recorded, and so we will post the recording on our website along with a slide deck of each of the two presentations so that you can take a look at those after the webinar as well. So I wanted to just say I'm very proud to be able to host this webinar for CHVA, and we're very happy to have both Andy and Michelle with us today to give us the presentations. So obviously you're here for a webinar on the F280 standard about how to right-size HVAC for net zero energy and net zero energy ready homes. And the description we gave was that using a right-sized HVAC equipment and ductwork will prevent on-off short cycling, prolong equipment life, and increase operational efficiencies, not to mention improve occupant comfort. Smaller equipment and ductwork can also allow for greater design flexibility, offering more living space. So Andy Oding, Senior Building Science Associate at Building Knowledge Canada, will address the key points of the standard, including why it's important that residential space heating and cooling systems have the appropriate output capacity, especially in low-load homes such as net zero energy homes, and how to calculate the heat loss and gain of homes for selecting the appropriate output capacity of space heating and cooling appliances. And then once Andy's done his part of the presentation, Michelle Côté, the Director of Business Development at Dettson Industries, will provide examples of their sustainable HVAC solutions designed to maximize residential comfort. So without further ado, I'd like to pass it over to Andy to get started with our presentation.
Thanks, Sonia. Hello, everyone. Hopefully today is not too much of a rehash for many of you. I actually see a number of you on the attendee list today that have likely sat through this before. So anyways, we'll try to make it a little bit helpful anyways. So we're strictly going to sit and talk about the F280-12 in particular, and then probably let Michelle take off on its application to some specific net zero projects. I'm in general going to speak about the application of the standard to low load homes and give you some examples. Again, many of you have probably seen this before in past presentations, but I want to give you some history and context as to the standard and why the changes and why the importance of it as well. So let me see here, make sure I get my slides working well. So you've all seen this slide. I wanted to take you a step back in time. Down at the left-hand side of the screen, we do have a, let me get my laser pointer in here. Can you see my laser pointer there? I don't know, Sonia, is it viewable on your screen?
It is, yeah.
Okay, good. So we have the 2012 building code, the 936, which Alberta is in the process of adopting. BC is quite a way ahead on. This is more or less where Ontario was in 2012 with the SB12. All sort of started out around this Energize 78 to 80. And as we move up the path towards net zero ready, which is sort of be an 88 to net zero 95, we see things happen to the home, one of which the loads are going to become smaller. Now, regardless of whether we move up this path pushed by the code or whether we move up it on our own through volunteer programs, the outcome is the same: low load homes that act funny. This is the National Build Code section, obviously, that sort of made the ground shake under our feet, if you will. 936, it was the first time really that we've ever seen in a code a minimum requirement for energy efficiency in a residential home. And I think the thing to note here is that down at the bottom you'll see that when the ERS, the level that's been placed or approximated in 936 was actually where our 2000 was in 2007, 2008, which is not that long ago. So we've come a long way in a short amount of time, um, and I think that needs to be recognized. This is a little sample of what's happening south of the border, just so we're not alone. Their scale goes the opposite way of ours. Instead of going up from least energy efficient to most on the EnerGuide scale, this actually goes from least energy efficiency being a high number down to a lower number based on the home energy rating index. And right now, their new International Energy Conservation Code 2015 places the standard building code home in the US at about a 55 to 60. And right now, I think there's about 7 states that have adopted that. There's probably another 20 somewhere in that are carrying the 2012 code, and a good portion of them still back in 2009. So in some ways, not a whole lot different than Canada, various codes, various places, but we all see where it's trending. You'll also see where the Net Zero Ready program in the States actually sits as somewhere here. So they are getting closer to that overall. 30 years ago, again, this is important to understand when we start talking about loads, this is what our home looked like. So we're 1982, long before Back to the Future was out and we drove DeLoreans around. This was what we used energy for in our homes. And absent in here, obviously, is this thing called cooling, but very large in this is that 75%, which was heating. Again, lights and appliances are what we'd refer to as base loads or plug loads, what have you, and then hot water at 15. So that was where our money went. That's where the energy was used. If we come up to today under current building code in 936 and also current building code in Ontario and some other places, we've dropped our heating. The load of the home has dropped. Obviously, more insulation is required now. Homes require more efficient windows, a little bit more fluffy stuff in the wall. Some codes address air tightness, whether it's through a checklist of observation, air sealing detailed by building code, or some require it to be tested. Either way, we're getting tighter. And heating's dropped to 55%. Hot water's moved up a bit. Lights and appliances has taken up some of that room. And we have this brand new one called cooling. Now, the interesting thing to note is when we're doing heat loss, heat gain calculations across Canada, which I see there's a representation of people across the Canada here, is that there are times that we're seeing this funny little load here, this 5% ends up using more energy and ends up being the reason for big ductwork and big fans and outstripping the need for that on the heating side. So that's a real funny one, and it's relatively new. It's also the reason that we build peaker plants or get rid of them or lose an election over them like we did here in Ontario. Typical Canadian household, obviously that's where the money goes if you break it apart. Now, if you're to take the net zero home and take it even farther, all of a sudden that heating load is now down around 13%. Hot water has dropped as well. And the big kahuna here to fry, the big issue is the base load. It's quite interesting to think that in most net zero homes that are being built out there right now, and many of you I see online have been intimately involved in this, is that 2/3 of the panels, the solar panels on your net zero home, are doing just your plug loads. So it's your iPods and your stoves and your fridges and your hot tubs that are real the worry, whereas if all it meant to be net zero was just to do heating, cooling, ventilation, and hot water and air conditioning, it would take about 1/3 of the panels, which is sort of interesting. So here's what we have. The status quo of where we were a few years ago before the F280-12 came in was when we did heat loss calcs for homes and heat gain calcs, we did not include the heat recovery of an HRV, which we have seen substantial adoption of in homes across Canada, and yet we were not including its efficiency in our heat loss calcs. We have also seen air change rates in homes drop substantially as well, now by virtue of building code addressing requirements for air barrier inspections, which are fairly new to us, and also volunteer programs. In some provinces, we're seeing programs like Energy Star hit 33% market uptake. Anyways, all in all, we're seeing air change drop. Keep in mind that these air change rates have dropped, and yet we really had no way of accounting for it in the old F280. And then you add to that the fact that our R values since 2000 have gone up by over 40%, and this is simply by code. So you look at this and you say to yourself, well, what should be happening to our equipment design and the size of our equipment? And the answer is an obvious one. Sort of ask a fifth grader, and they'll tell you it should be getting smaller. Maybe we should be heating some homes with candles. But anyways, um, here's what has happened though. The codes jumped in all zones for energy efficiency. Programs like Energy Star pushed the envelope. We have net zero homes being built. We have R2000 out there still being used. And what we started to see happen is when you cannot account for things like heat recovery and you cannot adequately reflect low air leakage in your heat loss heat gain models, and you cannot adequately account for below grade heat loss or for ventilation, is that when you start to increase these things in new homes, that the old way of doing calculation simply doesn't work anymore. And we started to see this, what we call unintended consequences in efficient housing, back in, I'm going to say 2007, 2008. Those were some of the early days of seeing Energy Star homes in Ontario. And the complaints that we were getting, that I was getting at that time as a builder, which were odd, was my new energy efficient home isn't comfortable, which is the last thing we want to hear. Now, it's not a trait of an energy efficient home, it's an unintended consequence of having to design a energy efficient home using an outdated standard for mechanical loads. So here we had shrinking loads, we had smaller fans, we had lower CFMs that were needed, and at the end of the day, we ended up with this thing called short cycling. And short cycling, the best way I can put it is it's like trying to run in your parents' shoes when you're 5. The shoes are big, they might be new, they might look shiny, but when you try to run in them, you get very sloppy. And that's the way oversized air conditioners act, and that's the way oversized furnaces act as well. When you short cycle during heating season, you start to get cold spots and severe stratification, because the furnace, when it does come on and the heat exchanger comes on, it hits its high temperature limit and it hits the thermostat, satisfies the thermostat and shuts off, and yet the fan never runs long enough to move enough air through the system on the longest run to either the back bedroom on the second floor or the good old rooms over the garage. We've seen situations where by the time the cycle shuts off, that the longest run in the house, which again is typically on the second floor or an outlying bedroom in the corner of the house, has only seen about 25 to 30% of its heat load met, because the air in the ductwork is still too cold. Meanwhile, the center of the house is warm. So cold spots. The other thing too is we see multi-stage units never coming off low fire. And in these multi-stage units and even fully modulating units, we've seen short cycling, and these things actually never come off the lowest fire. And the problem with that is when when your brand new furnace that costs you $5,000 more to purchase because it has full modulation, when it comes on, the thermostat in the hallway tells it can keep shutting off after 5 minutes. It also goes to lowest fan speed, which means we're now running CFMs trying to move air through houses with only about 300 CFM of air with ductwork that's sized for 1,200. Air conditioning, the short cycling doing cooling operation does a couple more things. Not only does it not get the conditioned air to the rooms, but because an air conditioner is meant to both cool the air and to dehumidify, the dehumidification mode, or the latent recovery mode in an air conditioner, typically is associated with a longer cycle. And when an air conditioner short cycles, what it does is it ends up blasting the house with cold air, but never running long enough to dehumidify it, and you start to get this cold, damp, cave feeling in your home. And one of the first signs is it's basements that are incredibly humid, and you start to get that wonderful smell where the rest of your house now smells like your old basement in your old house did. All happening in new energy efficient homes. Mr. Doug Terry, we did some work with his homes. Doug is a Zone 5 builder. The reason we did his homes is Doug's been a very energy efficient builder for years and was starting to have issues in these homes, again with stratification, complaints about comfort, and also the fact that he could not get the house balanced. And of course, we know the very technical strategy for balancing registers in most new residential homes is the manual turning open or closing of the dampers. And even when Doug tried to do that, like many of us tried to do, the home still would not balance, and we'll talk about why. When we looked at Doug's calculations under the old F280, which was called the F280-M90 because the last time it was done was in the 1990s, we found out that on average, some of these homes are oversized by 70 to 80%. This one house in particular was oversized by 126%, and if you look at the rest of the models under Doug's in his excuse me, in his lineup, we saw homes from 46 to 126. Now let me take you back. Rule of thumb in the old F280-M90, the rule of thumb was do not oversize for heating by more than 40%, or you might have issues with short cycling or discomfort in the home. And again, that was just a rule of thumb. Let's go forward here if I can figure out how to do that. So the new F280-2012 was published in 2012. It took until about 2014 for it to be referenced in Ontario and some provinces. It was officially referenced in the National Building Code, so for those provinces where they reference 936 in the NBC Part 9, it does very specifically call out the F280-12, the most recent version, so this is the one that you're under compliance for. The old one, the N90, 25 years ago, in reality, it had little changed in, I'm going to say 20 or more years. It had a very poor air tightness metric. When I say poor air tightness, it was based on an air tightness algorithm out of California that the US still uses, and no ventilation metric whatsoever. So the old M90 actually did not account for ventilation air. That was only added later by associations like HRI or TECA that said, hey, you might want to add ventilation into your load calcs. It also had a very poor window metric and a poor foundation metric, mostly because we were just starting to understand in the 90s how heat was lost out of foundations, or at least share some of the information. So if we look at a typical house in 2012, or the National Building Code today across Canada, this is where the heat is going. 55% is through heating. When we dive it down into that 55%, we see that the largest majority of it is actually through air leakage and ventilation, which is why this is a big deal that our load calc should reflect this. The old M90 ventilation was not included in the calculation. Even when you did use a heat recovery ventilation device, you were not encouraged to include the recovery of the HRV or ERV in your calculation. Later on at some point, I think the appendix did reference it, but many of the trainers and associations that used the old M90 were a little unsure of it, so they didn't recommend it to adjust that it be used. It also said that not for ventilation, but for natural air infiltration, or what we would call unintended leakage or air leakage, that our minimum default was a 0.3 natural air change. Now, everyone on the line is likely used to what we call air change of 50 pascals, which is your blower door test. This is quite different. This is what we call the natural air leakage, which occurs on average on a house over the course of a year just based on pressures, most of it being stack effect. To give you an idea, what does this mean in a house? Well, when we've been applying 0.3 natural air change as a minimum for almost 95% of the homes in Canada for the last 20 years, it's like assuming that on a 2,000 square foot home, we've had about a 350 to 400 CFM bathroom fan or range hood on full speed on the coldest day of the year, which quite frankly we know is way overcompensating. So if we do a quick analysis here, we've got, let me just see what I called this so I can see my whole screen. We've got your coastal cruising in BC. We took a 2,200 square foot home. We've got Big Sky, sort of Alberta, Edmonton Zone 7A. We've got your Big Smoke, Toronto area, and then we've got the folks down home. If you took what we were doing in those homes based on old codes under the old F280, we'd be placing these size furnaces in homes. So, 100 out in Zone 7A, 7B, probably an 80,000 in Toronto. And if we simply put an HRV in these homes and we take them to 3 air change, which the code assumes is the minimum on a single detached, we drop in some new windows, double glazed low E argon, we insulate the basement walls with R12, your loads drop from a 68 down to a 40. In Toronto, out west, you go from 105 to 69. Coastal area zone 4 is 46 down to 30, 74 to 39. Now the reason we show this is principally to make the point that you have to understand that for the last 30 years the smallest builder grade four-stair furnace, single stage on the market was actually about a 40,000 BTU furnace. That said, that means now code-built homes across Canada, there is only one place really in this nation that they should be selling anything over a 60, and that is in Alberta, and that's on the rare occasion that they're building just a code. Excuse me here. If we drag, let's take these numbers down further. Let's take the Zone 5, Toronto, Hamilton area, Zone 5. Of the 68,000 BTUs, 27,000 was the air leakage component based under the old calc, and ventilation was 16. And you'll see that when we apply a 3 ACH is tested with a blower door, all of a sudden we drop threefold down to 8,000. And we put an HRV in at 65% SRE, and all of a sudden we're down to 2,000 versus 16. So you can see one of the reasons for the big principal change. The new F280 has embedded spreadsheets, which is important to understand. It's the first time a CSA standard has had that, so you actually have to use these calculation spreadsheets embedded in the standard. And it uses a new calculation for air leakage, which is what HOT2000 has used for years, the Alberta infiltration model. New way to do windows, new way to do foundations, some sizing limits have changed, and so on and so forth. And if you're losing sleep and you can't sleep at night, go to the Appendix B and read it. It gives you an idea why things have changed. It's actually a very good narrative that was done by the authors. The one thing to be very clear, because there's been a lot of misperception, I guess, about what the CSA F280 is. Number one, it does not do air system design, and it does not do radiant design. All it does is give you a load. It does not tell you what equipment you should select, and it does not design your ventilation system for you, and it does not have installation guidance, and it does not require any energy efficiency level of any kind. It simply tells you what the heat load is and what the cooling load is. That's it. To do these other things, you have to move to different standards or to different areas within the code. One of the major changes is that in the new F280, little spell check there, F280-2012, is that the recognition for ventilation is no longer for total ventilation capacity, which is what we've been sizing it to in the past, but is now principal ventilation capacity. And that, by definition, is the ventilation that's intended to be delivered on a continual basis to a home. What this means is we used to be sizing homes based on 150 to, in some cases, 220 CFM. Total ventilation, range hoods, everything, plus now we know we're only sizing it to what's required as the principal. So that's a big difference. Heat recovery or energy recovery, ERVs or HRVs, are credited. So based on the ASE, not the SRE, but the apparent sensible effectiveness, we can include it in the calculation and get credit for it in our load calculations. The air infiltration is done using the Alberta infiltration model. Air leakage is now done the way houses actually leak in Canada. And I can't stress this enough, because for the last few years, in the last 20, 30 years, we've been doing it the way, no offense, we've been doing it the way the Americans have been doing it, using the Lawrence Berkeley laboratory method that says when a house leaks, it leaks out all holes equally all over the place. However, we know that 75% of the year our houses leak like this, which is in the center, which is a stack effect, which means that the air is actually leaking out some holes and leaking in others. So what happens is, in the new calculation, we assign the load to the rooms where the air is actually infiltrating, which means in our climate, magically enough, we're going to be assigning more heat load, or the need for more load to be met in the basements, and which may be one reason why we've not been assigning enough load in the past, because we've been doing it like they do in California. Air leakage, it also allows direct entry of blower door test results, which is sort of cool. What it basically does is, if you look on the screen, this is actually a sample of the drop down that the designers use. They put in the area where they live, they put in the building site, they put in the tallest height of the peak height of the building versus grade, they put in the volume of the home, and they can either do a default of air tightness, which in most cases they're instructed to use 3.57, which is a typical new code-built home, as a building code, or if they know what the air leakage is, say for an Energy Star build or otherwise, they're allowed to use the ELA and put in their blower door test data, which is sort of cool, and it gives them the calculation for the load in the basement. Embedded spreadsheets, the output of the spreadsheet, it becomes a multiplier, which you then apply to the air filtration. Just to give you an idea here, I did a quick for the zone 4 to 5, two-story single detached, 1,500 volume, it's about a 2,200 square foot home, 55-degree delta T. If we were to do a typical loose house, 10 ACH, we would have been putting about 12,000 BTUs worth of air leakage into that house. So an old farmhouse in the country, that's what you're going to have to add to that house just to keep up with air leakage. If you're a code-built home, you're about 4,000, and if you're an R2000 builder, again, you drop that in half, and that's the number that goes into your calculations. So pretty significant difference. Your air leakage and ventilation, the summary is air leakage does matter, so know what your air leakage is and give it to the designer. If your designer is not asking for it, there's issues. The Alberta infiltration model reflects how houses leak. Ventilation applies principal ventilation, and you can now take credit for your recovery. So that's a brief synopsis of air leakage and ventilation. Foundations have changed a little bit. We're now using a calculation that's based on the base imp, which is, again, what HOT 2000 uses. And basically what it does is it gives a much more broader, more accurate depiction of heat loss from below grade with all sorts of different assemblies that can be modeled. And this is the spreadsheet that's used. Some of you that use HOT 2000 will recognize some of these inputs. And it's simply more accurate. So number one is we know the ground is a heat sink, so get over it. We're going to have to account for the heat that's lost. Orientation of the insulation, outside, inside, above the slab, below the slab does matter. There's two different spreadsheets, one for slab on grade and one for basements. Windows, a few things that we do know is we're getting a lot more glass. Triples are coming very quickly in a lot of zones. U-value does matter. Coatings matter a lot. Solar heat gain number is incredibly important, and we can't ignore this thing called condensation potential. Solar heat gain has a tremendous impact on air conditioning loads, which is why in the new F280 we now do this thing called the transparent heat gain multiplier. It's a very fancy acronym for something that actually is quite simple. It takes into account your solar irradiation, your latitude, the place of your house on the face of the earth, and its orientation to the sun. But most importantly, the point I want to make here is the biggest number in this calculation that the designer has to do is this funny thing called the solar heat gain coefficient. He's ignoring your ER rating, so don't worry about it. Give them the solar heat gain number, because that number alone will affect your load substantially, and I'll just show you how. On a typical house, you've got 200 square feet of glass. I'm going to put you in Vancouver at a solar heat gain of 0.6. We have seen glass with that high of a solar heat gain. That means that you're looking at tonnage for glass on that side. You're looking at almost a full ton of cooling just for that kind of glass on the south side, southeast, southwest side of the building. If you simply change your solar heat gain for literally no cost for most window manufacturers, all of a sudden you're going to start to see the size of your tonnage change from 12,000 down to 8 and less on other sides, and that's by simply going with just a standard 0.4 solar heat gain, which still falls on the high side. If you want to go with a low solar glass in the house and go with something around 0.21, all of a sudden you're down to a third of what you originally were with a high solar gain glass. And if you think this through as you move through the calculations, it's why it's number one, it has such a big impact on the wall. So keep in mind when you're designing homes that when you're doing heat loss, heat gain, that if you have a 15% window to wall ratio, having triple pane windows is actually going to reduce your loads better than putting in, say, 2 inches in some case, or 1 inch of continuous insulation, R5 or R10. So windows are important. Solar heat gain, that number is not only going to drive the cooling load, but your cooling load will drive your CFM requirements and the fan size, which in effect drives your furnace or air handler size, which then drives your duct size. So, be careful of high ER. And again, optimize U value and solar heat gain. We would say ignore ER, even though it's a code compliant number, and going forward, start to look at U and good solar heat gain numbers as a whole. I'll skip this quickly. The new F280 actually uses effective R values now. They use it out of 936, so it's done the same way the National Building Code does it, and Energy Star and other provinces as well. There are some appliance load updates, but nothing earth-shattering. There's been some small tweaks to the calculations for internal gains. If you do F280 2012 and get a room by room, and then you do HOT 2000 and you do a room by room, you'll notice that they're similar, but they're not exactly the same. However, they're much closer than what you would have got under the old N90. Equipment sizing limitations. This is a conundrum. The new CSA standard basically says that a building room shall not be less than 100% of the total heat loss for the building in each room. It no longer has the restriction of you cannot oversize by 40%. And on cooling, it says that it must meet 80% of the load. So this is a bit of a conundrum for some folks that feel strongly about the oversizing issue. And the reason is that the committee felt against, because of a lot of examples, heat pumps, combo systems, window glazing, that they needed to leave the designers some flexibility. They may use equipment that's capable of larger loads, but oversizing may not be an issue because that piece of equipment may be fully modulating, and it might be used for two purposes. It may be used for space heating and for domestic hot water. So again, that's changed. Real quick in action, this is a couple, some sample homes we've done. This was a house that a builder had built, and they wanted to move to building better than code, so they went from 80 to Energy Star 8283. They used the new F280 in the house. This is a production builder. Originally, the house had about a 46,000 heat loss on it, 93% efficient furnace with 22 by 8 size trunks with 5 to 6 inch mains. And when we redesigned the home, the total combined heat loss dropped down to 28. That was with a little bit more insulation, using the new F280 and using better air tightness, 2.5 ACH when tested with the blower door. So all of a sudden, we had to use a two-stage unit just to enable the lower stage to meet the main load of the house. The big thing here, I think, though, that's interesting, and again, won't be like this burn, but we actually ended up with 5 fewer supplies, 1 less return. The duct went from 16 or 22 by 8s down to two 12 by 8s, and the runs went down to 4-inch apiece. The installers that did this house refused to install the house until we actually came on site and reassured them that it was okay for them to do it. When we tested the house, it worked fantastically well. We had better static pressure in the system. We had better throw at the diffusers. We had better mixing, and we did it all with no noticeable increase in noise. And we had great cycle times. I'm going to skip some of this because Michelle's going to show it to you. A couple things I want to bring out. Here's a sample of a 2,300 square foot home, moving to EnerGuide 80 new code, moving to R2000, future Energy Star, net zero ready. You'll see loads drop substantially. You'll see heat gain loads drop as well. It's all good news for the homeowner, but then it gets a little funny for the designers because all of a sudden, we now also see a smaller fan size. As we move from BTUs to lower beat loads, you move from higher CFMs to lower CFMs, which means you have to have smaller ductwork and you better seal the life out of this ductwork. So if we can get anything across today, it's that low load homes will require the ability to move lower CFM more often, if not continuously, in homes if you're using air delivery comfort systems. This is why we have to change our language. We have to start to understand the difference between displacement and dilution. Displacement is the method of conditioning we've been using for 30 to 40 years plus in the residential market, and that is air that comes out of a register. It comes into a room and it displaces air, and the displaced air magically goes down the return. The return does not pull the air around the room. The register does not throw air around the room. It is heating by displacement. Dilution is heating or cooling conditioning by mixing the air in the room. And so small loads equals small air volume. Displacement air management can be incredibly tricky, especially with low loads and small volumes, because you'll end up with stagnant areas in the home. Dilution makes more sense because now you're mixing the air and you're properly tempering the air. When you move to continuous low to mid-volume CFM systems, you start to maintain temperatures in every room and you increase ventilation effectiveness, which means the fresh air is more consistent across the home and relative humidity is more consistent. Your low temp air supply and higher R value surfaces are fine. When you start to add R value to these walls and you have better windows, you start to change the old mantra that you got to get a register by the window because those walls are in fact warmer. You still have to get some mixing, but if you can push the air a little bit with throw, you can then mix it against the wall. Um, Dilution versus mixing. This is what happens when you heat with displacement, which is what we've been doing for years with low CFM. And of course, as we get more efficient homes, lower CFMs, the stagnant area is going to get bigger, both during heating and cooling. If we manage it by diffusion or displacement, we start to mix the air in the room and the homeowner starts to feel warm all around. A couple additional items. Part loads are king. Low load houses, Code Built, Energy Star, Net Zero, R2000 are all low load houses. These homes will likely never operate at high load unless the Joneses open all their windows in the second week of February and have a party. These low load homes do not need setback thermostats because the setback thermostats simply do not work, but they need smart thermostats. They need low speed continuous air or room conditioning as an ideal. So set it, forget it. Sealing of these systems is incredibly important. When you have low CFM systems, low continuous movement of air, you have to make sure that you maintain good static pressure or it's never going to get to the longest run. So sealing the ductwork is incredibly important. When you seal ductwork, it makes balancing the system effective. If you try to balance a duct system that's leaking, it's like trying to plug the holes in your garden hose so you get more flow out the end, and we know from fluid dynamics and mechanics that that doesn't work. It just simply goes out the other holes first. You can't balance a sieve, like we say. Lots of new opportunities out there, dual fuel applications, gas plus air source, they work incredibly well together. The next thing to know is there is challenges with the building officials and with builders and designers. There are standard designer information sheets embedded in the F280 that you can use that are meant to be used at the desk when you do your building permit application. I'll show you a sample of that. That's what it looks like, and that's what the building official can expect. It's filled out by the designer. The designer puts his logo, his qualifications, his HRI number, whatever you have them doing it at, or engineer stamp, and they simply show what they're using as opposed to sending them 46 pages of documentation. So beyond this, going forward, a couple of things you're going to need to know. Houses are more efficient, loads are dropping. Make sure you test and monitor. Know what your air change rates are in house. Know your blower door values. Know what your cycle times are in some of your furnaces. It takes a good certified energy evaluator less than a half hour to figure this stuff out. You know that windows are critical to the size of your ductwork and solar heat gain. Air tightness matters. Good duct sealing is going to make a world of difference. Part loads are king. Heat recovery, now you're getting credit for it, and start to move on from just having good returns to actually have good registers and diffusers where you actually get throw, heating the home well through diffusion. Thank you.
Thank you so much, Andy. That was wonderful. And I know that we do have one question here, but we're going to move right into Michelle's presentation, and then we can answer some questions at the end. So I'm just going to go ahead and make Michelle the presenter. So go ahead and put your screen up when you're ready, Michelle. Perfect. Thanks so much, Andy. All right, Michelle, go ahead.
Thank you. Okay, so I'm having some sound challenges, so I'm going to play a video first, and then it will take me a couple of seconds, and then you guys will be able to hear me speak after.
Depending on where you live, the old creaky furnace in the basement has almost become a cliche. How big are these things anyway?
These things use up a lot of fuel, and they take up a lot of space. I don't even know how they got this thing down here.
Right? You know, these monsters are a thing of the past.
Yep, new furnaces are smaller and more efficient than ever. And leading the way is the Dettson Chinook, giving you the right size system for your home.
Ron, I'm freezing.
You know, 5 minutes ago I was sweating. This furnace can't seem to keep the right temperature.
Well, that's what you get with the furnace. The thermostat reads the temperature, and when it gets chilly outside, it tells the furnace to turn on and start blowing hot air.
Yeah, until it gets too hot.
That's right. The furnace keeps blowing hot air until it reaches the desired temperature. The only problem is some of the rooms in the house get really, really, really hot.
This is what's called an overshoot. The furnace shuts off, the house cools off, but the furnace doesn't turn on again until the whole house reaches a certain temperature. And by that time, well, I'm sure you can guess.
Ron, I'm freezing. This can't be efficient.
You think?
Right?
The houses are getting more and more tight and well isolated. So if you have a 45,000 BTU unit, that's in a house that's sized for a 15,000 BTU unit, well, you're going to have some big overshoots. And that's a problem because it's going to be very uncomfortable for the homeowner.
The Chinook runs a lot slower for a lot longer. It's sort of like using a roundabout when you're driving. Starting and stopping your car's engine will use your gas up. However, when you're on a roundabout, you may slow down, but you never really stop. So your fuel efficiency goes way up, sort of like the Chinook.
And with houses being built a lot tighter and much more energy efficient, there's little need for these big honking furnaces down in the basement.
The folks at Dettson call this philosophy a right-size system. And now, many of the advances that have been made in their heating systems are starting to be featured in smaller cooling systems too.
Okay, hopefully everyone can hear me okay?
Yep.
Perfect. All right, so thanks for having me today, and some of this will be a little repetitive from what Andy said a little earlier, so I'll try and fly through this as fast as possible. So basically, we know that we solved more than one problem, a few problems. So we talked to builders, engaged industry leaders and consultants and building scientists, but most of all listened to builders and said, what are you guys having challenges with? What do you need from an HVAC system moving forward? And identifying what our environment was like. So obviously we're meeting higher efficiency requirements in building codes, voluntary programs. Now we've got net zero energy. We know that, as Andy said, those high performance loads or high performance homes have lower loads, and it was more and more difficult to find gas equipment and forced air traditional systems that had equipment small enough. So we also wanted to address comfort. So comfort does not only include temperature anymore, it includes noise, it includes humidity management, and Andy said short cycling and overshooting just isn't cutting it. We know that square footage is more and more of a premium, and mechanical footprint is right in that equation. And then on top of that, when you start talking about innovation, when you start talking about modulation, we know generally that builders say, okay, that sounds like it's expensive. So builders asked us, can you please help us find money to offset the cost of moving to modulation? So typically you might see a 30% jump from one stage to two stage and another 30% from two stage to modulation. So, so we've got customers expecting thermal comfort at all times and helping builders get there. And I always like to use the terms better, faster, and more cost efficient. And more importantly, at the end of the day, we need something that our homeowners, it's easy to operate, it's not scary looking, and the whole premise that we've been hearing constantly is set it and forget it on the thermostat. So let's talk about that short cycling and overshooting. So we did a 2,600 square foot house. We tested it. We wanted to know how long it took to condition the air from the main trunk of the furnace out to that last register in the house. And just to hit the delta T in that 2,600 square foot home, very high performance, it took over 14 minutes. So we knew that that's why overshooting and short cycling was giving us a problem. So how do we do better? So we looked at creating a low CFM, longer cycle system. So looking at the modulation, driving less callbacks with comfort and balance and noise issues that Andy talked about, reducing and optimizing the mechanical footprint, and show me the money. So giving a better system at a competitive price, and flexibility for energy usage. We've got regional preferences and needs across the country, and also for those builders striving for net zero, passive house, those above and beyond programs that might be going to electric only, for example, with net zero and solar PV. So we introduced the right size system. So looking at heating and cooling, so together we call that, those two systems together, the right size system. So when we had the formula down for the furnace, so the Chinook line, so driving that low CFM over longer cycles, we wanted to take that same concept over to cooling. And to do that, we couldn't select a traditional air conditioner. We had to hang our hat on a heat pump. So it's a side discharge, inverted technology, and again, very quiet. Both of these equipment run under 50 decibels. And so the whole driver is low CFM, longer cycles. So get that modulation introduced into both heating and cooling seasons. So you can see the cooling unit on the outside of the house there. And so this is typical of what we would see no matter what mode this is. This just happens to be cooling. But typically what we'll see is the CFM, the green line at the bottom. So this is over 12 days. We'll typically see the systems not running over 300 CFM in heating and 350 CFM in cooling. We'll always see, as long as that system's right-sized, it will run between 40 and 60% of its capacity. And the pink line at the top, that's what we really like to see, is a nice, consistent indoor temperature while you've got that dark blue line, which is the outdoor temperature ranging from 8 degrees all the way up to 28 degrees within that period of time. So we want to see a nice balanced indoor temperature over that span of time. And so this is a good graph to show you how that temperature was all over the place and inside nice and balanced. So the other benefit that we were able to see back a couple years ago, we were monitoring Doug Terry's house, and so if you look at the top left, we could see the difference between the relative humidity in the home and the temperature. So we all know there's a correlation there if with temperature and relative humidity. But from a new construction standpoint, we don't want to see that variance for reasons of nail pops, wood warping, etc. We want the house to be at a nice balance. So when we looked at that, and the engineer said, well, hold on a second, that doesn't look like what the concept of the design was. We realized that there was a setback on the thermostat. So we called Doug and said, hey, turn that setback off on the thermostat. So on the right-hand side, you can see now there's a nice balance between the temperature in the house and the relative humidity. Doug brags about he can change the relative humidity in his basement by 8% overnight, so that's it on the top left. And after the setback came off, you've got a nice balance there in the house. So yet again, addressing those comfort issues and the humidity management. So when we can drive humidity management, especially in cooling season, if you're short cycling, that system's turning on and off, and as soon as it turns off, you're uncomfortable again, and when it's on, you're likely freezing. So we want to just keep a nice balance, so driving that low CFM, longer cycles. And a really good analogy is when you're driving in the car, or you get in your car in the winter, it's freezing cold, you've got frost all over the windows, so you get in and you crank the heat to full blast, and you turn the fan all the way up to 4 if you're in a manual car. So then you get out, scrape the windows, get in the car. So you want to start driving, the windshield's clear, but there's no way you can drive because the fan's on 4. So you're going to probably dial the fan back to a comfortable 2, but still the heat, you're going to have it cranked. So then as you're starting to drive, and you're getting to temperature, you're never going to turn that fan off. You're going to turn it to 1, and then as your nostril hairs are catching on fire, that's when you're going to start dialing the heat back. So a modulating furnace does all of that for you. It's like the brand new cars where you hit the temperature of 21 and the car does everything that you want. So that's what we want out of an HVAC system. Just set it and forget it, and have a nice balance, temperature and relative humidity in that house. So then we wanted to address HRVs and ERVs, so that continuous airflow in the home. So we interlock in, cap the CFM at 200 CFM, so no matter what mode that system is in, you've got continuous airflow. So with this system, you've got an enhanced ventilation system, driving balance and humidity management, and driving a healthier, quieter, and more comfortable home, period. sorry. So after we figured all of that out, then builders said, hey, we've got multi-residential product, smaller square footage. Can you guys go even smaller? So we did. So we've got a 62-pound fully loaded 15,000 BTU furnace that modulates down to 6. This is perfect for one-story construction. It throws a little less CFM than our regular 15,000 BTU furnace that modulates down to 6. And so we're seeing unique installations. We've got a builder that's never had mechanical space before, so they've built a kitchen cabinet looking system in their kitchen to put the HVAC system in, and then we've got these things can go in horizontally, so looking at maybe space above the stacked washer and dryer. So really perfect for the newer multi-res product. We also wanted to look at distribution. Andy kept repeating the term low to medium velocity. So we had lots of complaints about high velocity systems. Please don't give us a high V system. So we wanted to make sure we stayed away from high V. And we wanted to address noise, so that sheet metal heating up and cooling off, the knocking and banging, that all adds to the noise. So we're building houses better. We can't hear the neighbor mowing their lawn anymore, but you can hear everything cycling inside the house. So we wanted to address noise. We also wanted to address that thermal balance. So how can we utilize the system, the modulating system, and get even better throw and better mix in the home? And we wanted to look at mechanical footprint. So could we reduce some bulkheads, get rid of some floor registers, look at spatial separation and the noise, one, the noise for spatial separation, and two, the mechanical footprint for mechanical separation in smaller square footage developments. And all of that time it takes for air leakage. So our system will absolutely work with a traditional duct system. Just get it under 10% leakage. That does take extra contractor time and detailing and labor, which equals money, to get that air leakage down in the ducts. So we wanted to look at that to help potentially, and this is where the show me the money part is, so help offset the cost of getting a better system, better modulating system, and offset the cost of doing that. So labor, detailing, consistency in installs, as well as just overall better systems. So therefore, cutting down the warranty callbacks. So our system, we install it 6 inches from the ceiling. Andy or someone is unmuted right now, and it's quite loud.
Yeah, Andy, if that's you, I don't know if you can mute your phone.
So, our installs are based on bringing everything to the interior walls of the house, cutting back on that sheet metal work, going all the way to the exterior walls. So interior, 6 inches from the ceiling. Our first rule of thumb is we try and get everything bathing the window. If we can't do that, then we will go parallel to the window, etc. So we've got a couple of rules to follow, but we're running off of 6-inch or 8-inch mains, and the smart ducts are 2.5-inch flex ducts. So what we found is we got better throw. So a traditional register gets 3 feet of throw for 30 CFM, and with the small smart ducts we got 9 feet of throw instead of the 30. So what that allows is us to take advantage of the quanda effect, so the air sticks to the ceiling as long as it can. It uses the ceiling as a main plenum, and with that 9 feet of throw paired with equipment that's running at low CFM over longer periods of time, you can see on the left the 3 feet of throw from a traditional system, and on the right 9 feet of throw with the low to medium velocity system. So much better mix and much better conditioning for rooms, and this is hugely important for, especially where we've had the problem children in the industry, right? The bonus rooms above the garage, stack effect for townhouses. So really addressing those issues and solving a lot of the problems that we were traditionally seeing. Let's talk about optimizing your design. So again, off of 6-inch or 8-inch mains, 2.5-inch flex ducts, we're able to get nice clean installs, and we've got guys using TGI. They're just pre-cutting holes through the boards, and the HVAC guys can just come in and feed through quite easily and simply. So there's also debris caps all the way through, so no chance of getting dust and debris in those ducts during install. And more importantly, we're getting 2 to 5% leakage and a much faster install and more consistent install. And so now you've got all that usable floor space. You don't have registers on the floor anymore. You've got those diffusers 6 inches from the ceiling that are getting better throw, better mix, and a much more comfortable system. So just some benefits there of the smart duct system. So we got the right static pressure, low to medium velocity, better throw, 9 feet versus 3 feet, better mixing, using that ceiling as a main plenum, better air leakage, 2 to 5% leakage, optimizing the floor plans, getting rid of expensive returns. Our system's efficient enough that you only need 1 return per floor. So getting rid of some costly returns, and also getting rid of some costly bulkheads, and just getting a better install and faster and easier for the contractors. And more importantly as well, and also included noise reduction for sure. So we solved the problem, competitive and innovative Canadian solution. We manufacture it of Sherbrooke, Quebec. We're Canadian family owned. We designed this system for high performance loads and low load homes as a result of conversations with builders, primarily like even Pulte homes down in the States that are in 19 different markets. So we really worked at with builders and their building scientists to understand what the needs were. Low BTU equipment, longer CFMs, longer cycles, low CFM, driving comfort, noise reduction, humidity management, optimizing those floor plans and mechanical designs, centralizing the ducts, reducing bulkheads and returns, energy flexibility. So we've got a lot of room to play there with an all-electric system, using the heat pump for heating and cooling with a backup gas, or using the heat pump for heating and cooling with electric backup. Actually not backup, shared load. So when the COP on the Alizé hits 1, then the Supreme, the electric furnace, would kick in and work together in a shared load capacity. All around better system, reducing callbacks and warranty issues, and also easy to operate, setting it and forget it. So that's the premise. On the cost efficiencies, just to recap, so you've got durability of equipment. So when you're using that brushless DC ECM motor technology, you've got increased durability and efficiency on that motor life. And so instead of turning on and off, you've got a nice, just gentle, like running an LED light bulb, so to speak. Reliability, so we use primary and secondary or stainless steel. There's a 20-year warranty on our heat exchanger, so we're giving quality components, and more importantly, it's not proprietary components going into our system, so contractors can trust and stock the parts inside. And then with duct design optimization, we'll work with duct designers, we'll work with contractors to help them optimize the design, and then working with the contractors to understand the savings on install time and duct sealing, for example, and just all around, hopefully bring together your construction department, your warranty departments to realize where the savings are on that side. And so Doug is using our system, Reed's Heritage Homes is using our system in their net zero homes. You've got RDC Homes, they're going to be putting in a prototype zoning system out in BC. Mattamy Homes has installed a zoning system prototype, and so is Reed's Heritage. So as we've kind of solved these problems, and we've already moved on to the next, so we're a little different than other manufacturers, pumping about 6% of our net sales back into R&D. So we're trying to stay ahead of your challenges as we move along, and hopefully that will help. And I've just got our contact information there. So I've got a colleague that manages contractor relationships and distribution across North America, and then I myself work with builders, HVAC designers, certified energy evaluators, and consultants. So that's it for me. Let me know if you have any questions.
Great. Thanks so much, Michelle. We do have some questions here, and I'm going to see if I can find some that are specifically for you. Yes, and then we'll see if Andy's still on the line, and we can get him answering. I know we've hit 4 o'clock now, and there's a few people who've had to leave, so we'll try and get these questions in quickly for those who are able to stay. So John's asking, code requires the ability to balance airflow. How do you balance airflow for the smart duct systems?
It's been designed specifically to be balanced, and that's part of our design guides that we walk the duct designers through and your contractors through. So right now we're supporting both duct designers and contractors. It's all part of that formula. So we know that we want no less than 7 feet, no longer than 25 feet off of the 6-inch or the 8-inch main. So we've basically formulated what we need, knowing that maybe each diffuser is going to have 25 to 35 CFM, and we know what each piece of equipment is going to throw CFM-wise. So it's really kind of taking a step back and understanding what each room in the house requires. So it's not just about there's no rule of thumb anymore about how many square foot and here's the size of your furnace. It's really getting your certified energy evaluator to spit out the room by room calculations when they're doing the energy modeling. And then looking at the duct design and saying, okay, how much CFM do we need? How much BTU do we need? And let's, based on our design parameters, deliver what each room requires through the design. And so we're balancing it from the design end, if that answers the question. And then once it's installed, then if you guys are working with energy evaluators that can and contractors that have the equipment to balance, they'll be able to do so. And then returns, they also design the returns as normal. As I said, they just don't have to. They can have one per floor.
Great.
I hope
Perfect.
that helped.
I think so. That helped me. I understood it. So if I did, I'm sure he did. And so we have another question here that I think is for Andy. Andy, are you still on the line?
Yeah, I'm sorry for the background noise, but I'm here.
Oh, no problem. We understand you're on the way to the airport. We have a question here about what is the role of the F280-12 versus HOT 2000 in designing new homes?
That's actually a very good question. HOT 2000 is primarily a energy evaluation tool, energy gauge tool, if you will, to assess or estimate the energy load and how the house is going to work or building is going to work. So it's talking about energy, and the space load for conditioning is only part of that metric. F280 steps away from that and says, we're not worried about energy efficiency, we just need to know what the load is. Can you do a simplified load calculation with HOT 2000? Yes, you can. We would always say, if you, in the absence of a designer not being qualified or able to do an F280-2012 calc or having the standard, the next best option is a room-by-room calculation using HOT 2000, 1051 or newer. But really the best bet is to use the F280 calc to be more accurate. So one's for energy, one's for space conditioning, two very different things.
And now I just want to actually follow up on that question, because I know that we're trying to move towards production builders being able to do this. So once we have a production builder getting a good feel for how those calculations end up turning out, will they eventually be in a place where less of that modeling has to be done up front because it does become more intuitive?
As far as model, are you speaking modeling for the energy or the calculation for the loads?
Well, I'm thinking for both, because if we're talking about production builders, they typically have, they've got their most popular models. So say someone may have 60 different models, but 6 to 8 of them are the most popular ones that they end up building more often. So if it's the same model over and over again, I'm assuming that they then become familiar with what the requirements are for those rooms and for the loads of the houses, correct?
Absolutely. Nope. And you've got an example of that, I'm going to say, in some markets in Canada and the U.S. where, codes or programs, I'm going to say mostly programs, are a little bit more mature. So production builders doing things like Energy Star, Net Zero, Zero Energy Ready. And what you find that a production builder that will have 40 standard models, once you do the heat loss, heat gain calcs on that house, and you can do them in such a way that sort of works in the area without oversizing it, the unit as far as orientation and everything else, that you can get a pretty good idea on one design how that house is going to work regardless of where it is. Now, obviously, if the builder takes model A, the loosey-goose model, and decides to add 15% windows, all bets are off. He's going to have it remodeled. But in general, I would say, yeah, in the mature markets, they have figured out how to do that.
Great. Okay, yeah, because I'm looking to, obviously the trades become more familiar with it and so on and so forth, that less time is required up front, and it just, you get used to it and you become familiar with it, right? We also have one other question. The person who asked it has already left, but I feel it's an important question for those who are on the call that are in the renovation market, because he's asking, what is the implication of the standard to retrofits, and do they follow the standard, and how about if you're retrofitting to net zero, what are the implications and or issues?
Okay, so this is an interesting one. So first of all, your building code is the first place you're going to go to find out what is required for load calculations with a reno. And jurisdiction is going to have their own take on that. But that said, in the renovation community, like the new for years, rule of thumb has guided everything. So the house is 2,000 square feet, it was built in 1980, typical house like that, and that area needs a 4-ton. Or I'm going to put 100,000 BTU in just. So you now need to be a bit more careful when you are doing a new mechanical system in a renovation, especially if the renovation is what we would call a gut rehab, which is most likely the case with the net zero renovation, because you're not really going to net zero on a renovation unless you're really addressing the entire house. And if that's the case, you absolutely need to do a new calculation for the mechanicals on that house. So sorry that the answer is not that straightforward, but the reality is gut rehab, net zero target, absolutely you're going to need it. If it's just a if it's just a one-off, a bathroom, or adding a sunroom, you may not need to, but again, check your building code and local jurisdiction, because they will guide you through it. Now, I will tell you that we have had some experience in renos and some other work we've done, that if you do a substantial reno, not a gut rehab, and you add some insulation and air tightness, and yet you're not tearing the inside out, and you're not redoing the ductwork, and you're not doing the mechanical, and it is an air delivery system, we have found that because you are lowering the loads, you can't shrink the ductwork magically, but you may want to consider sealing the ductwork. And the reason for that is at least start to get the air where it needs to go and keep the pressures up in the system. There's lots of ways you can go back in and retroactively seal the duct system. I'm not going to speak out because there's lots of proprietary companies that do that, but it does seem to have some benefit on the retro side in energy efficient renovations.
Great. Thank you so much. And we're out of time. We're actually past time. So I wanted to once again thank both Andy and Michelle for their great presentations. And their contact information was posted. So if you have further questions, I'm sure that both of them would be more than happy to help. I will be posting the recording of the webinar as well as the presentations up on our website. Same places where the registration link was. So if you have any further questions, please don't hesitate to contact me directly, and I'll help you out where I can. Thanks so much, everyone, and have a wonderful afternoon.